Hey everybody, my name is Scott, and today we're going to solve the maximum subarray problem on LeetCode. This is a pretty familiar problem to a lot of people. It's a common problem you see pop up in different places, and we're going to solve it using dynamic programming. So let's go through the problem definition. It says find the contiguous subarray within an array which has the largest sum. It's a very straightforward definition. Alright, so if we're going to solve a dynamic programming problem, we need a recurrence relation, right? We need to come up with an equation which writes the solution of the larger problem in terms of solutions to the smaller problems. Now, the recurrence relation for this problem isn't immediately evident. It can be a little difficult to see, especially when we're talking about these contiguous subarrays. Because obviously a contiguous subarray is going to have a beginning index and an end index, and how are we going to keep track of all that in some sort of a recurrence? I thought about it for a little while and eventually stumbled onto the recurrence where the maximum subarray, and for the recurrence relation we're going to have arguments of the numbers, the number array, and an index I is equal to the max subarray, if the max subarray from the number array up to index minus 1 is greater than 0, then it's equal to the max subarray of the number array up to I minus 1 plus the number at I, else it's just the number of I. So that's a little strange at first to think about it intuitively though. Let's say we're at an index I. Let's just say we're in this array, we're at this index, we're here at 4. And we're trying to determine, okay, what is the maximum subarray sum from 0 up through this number 4, from the beginning of the array up through 4. Well, thinking recursively, if we know the solution up to here, up to this index, then we've got something we can work with. So we have two cases. If the maximum subarray up to this index, the index of -3, if the maximum subarray is less than 0, then what must that mean? That means from the beginning of the array, up through this index, the maximum subarray sum is negative. Now what else must that mean? It must mean that we never want to include it in this answer. We don't want to add this number to a negative number, okay? So that covers the first part of our recurrence. And if you think about it logically, it makes sense again. We recursively solve this subarray here, and if it's negative, then what that must mean is we never want to add this number to it, because then we're just making a negative number more positive, and that's never going to end up being the maximum number. However, if the maximum subarray ending here is positive, then what that must mean is what we will always do is add this number to it, because in that case we're making the number more positive, a positive number more positive, and we're increasing the maximum subarray value. It's a little confusing to think about at first. I had to think about it for a little while, why the logic and the math makes sense behind that. But once you understand it, it begins to make sense. And the key is that it's a contiguous subarray. The sub problem that we're solving is the contiguous subarray from 0 up through the previous index. So the contiguous property is satisfied because we're only considering the next element. That's key too. I was struggling with figuring out how we were going to make sure that the contiguous subarray was satisfied by always considering just this value. Well, by considering this value and the subproblem that we solve is up through this index, then this index is contiguous with the subproblem, 0 up through -3 here, okay? So that's how we make sure we're still contiguous. And again, if the recursive solution up to the previous index is negative, then we will never consider it. We'll just consider the number here. However, if it's positive, then we can always add this number to make it bigger, right? If the solution up through here is positive, we can always add this number. So that's how the recurrence works. Now let's implement it. Most of the dynamic programming videos I've done so far have been memoization. I worked on a memoization solution for this problem, and it turns out that tabulizing the solution is much easier. So memoization is solving the problem from the top down. Tabulization, we're going to build it from the bottom up. And I'll show you what that means. So to start out with our table, we're going to make an integer array. We're going to call it DP. It's kind of a common convention standing for dynamic programming. We're going to set that to be an integer, the same length as our input. Now, the one thing we want to do in this problem is keep track of the maximum that we've seen so far. We're going to initialize that to the initial value in the array. And why are we doing that? Because we don't want to scan back through this DP array to find the maximum again. So we can keep track of the maximum here, and the solution we're building may not necessarily include the last index. So we're going to keep track of the maximum value that we've seen. The maximum, and this max stands for max subarray, sum that we've seen. And then we're going to initialize our dynamic programming array of 0 also to be nums of 0. Alright, so we're going to loop up to the length of the array. And what are we going to do? Well, this is basically, if we were memoizing, this is the recursive call here. Except since we're building it from the bottom up using tabulization, all we do is look at the previous value. And that's why we're saying it's being built from the bottom up. We're tabulizing the values, and then we're building the next value based on the previous value. And this is where we implement the recurrence that we came up with. Okay? So if the dynamic programming solution at I-1 is greater than 0, okay, so that's what we were talking about. The maximum subarray sum up through the previous index is greater than 0, then what we will always do is add the current number to it. So dp I-1 max subarray sum through I-1 plus the current number, nums of I. If it's not, if that value is negative, the max subarray sum through I-1 is negative, we never want to consider it and include it in our current value. It will just be the current number, nums of I. And then we have to update the max we've seen. So dp of I, which is our current max subarray sum at this index, if it's greater than max, then we're going to set it to be dp of I. Else it's going to stay max. Return the max. Alright, let's see if we have any syntax errors or anything by running the code. And while we're waiting for that to do that, again, this is called tabulization. Most of the dynamic programming videos we've done have been memoization, where we write some sort of recursive function. And that's helpful because when we come up with these recurrence relations, runtime error. Index out of bounds. What did we do wrong? First off, this should be 1, and that should solve that. So we needed to start this loop at 1 because we're checking I-1 in each of these. Obviously, we can't check -1. Alright, so got the right answer there. Submit the solution. And we got an accepted solution. Okay. So to recap what we did, came up with a recurrence relation that solved the problem. In this case, it was the maximum subarray of the number value up to an index I is equal to the maximum subarray of that array up to the previous index, I minus 1. If that value is greater than 0, if it's greater than 0, then that means it's a contiguous subarray with the next index. And if it's positive, we're always going to add the next element to it, because that makes it bigger. We want to consider the previous subarray sum because it's positive and it will make our number bigger. If it's not positive, it's less than 0, then we don't want to consider it because the current value is going to be greater without it. So we just set it to be the current value. That was our recurrence relation. Usually we write a recursive solution and then memoize it. Like I said, I worked on that a little bit. It gets a little hairy for this. So this is tabulation. And tabulation is you set up some sort of way of building it from the bottom up. Now, some people will say we could actually do it without this array because we're only considering the previous value, which is true. So we don't necessarily need this. It makes the tabulation explanation a little more explicit though. So a lot of times you're going to set up an array, some way of remembering your previous answers, and then initialize those, and then we loop through the array. And this is the implementation of our recurrence relation. So the dynamic programming solution I, the max subarray sum at I, is equal to, this is a ternary statement, and what we're saying is if the max subarray sum of I minus 1 is greater than 0, again it's positive, that means we want to include it in our with our current number. It'll be dp I minus 1 plus nums of I, because nums of I will get bigger. Nums of I will get bigger because this is positive. Else, if it's negative, then the dynamic programming solution, the max subarray sum ending at I, must be just nums of I, because if it was a negative value, whatever nums of I is, it will get smaller if we add it to it. And then last, all we have to do is update max. If we've assembled a solution greater than max, then we set it equal to the max. So that's it for this one. It's our first tabulation solution. A little different. It looks a little different. Going from the recurrence relation to the code isn't as explicit and simple, but there are advantages to this. It's a little more straightforward because we don't have a bunch of function overcalls like we do with a recursive solution. So you're saving the function overhead time, which is good. And in problems like these, when your solution is so tied to like an index type thing, it can be a little easier to keep track of indices and things like that doing it this way. That's it. Hopefully you enjoyed the video and learned something. We'll see you next time.